Today's speaker is Mark van der Laan, the Jianping Xu Carl E. Peace Professor of Biostatistics and Statistics at the University of California, Berkeley. His primary research interest is developing statistical methods to estimate or learn causal and non-causal parameters of interest based on potentially complex and high-dimensional data. To develop and refine these methods, he works with simulated and real data in collaboration with biologists, medical researchers, epidemiologists, and others. He also developed the targeted maximum likelihood methodology. Mark is a founding editor of the Journal of Causal Inference, and today he'll be speaking to us about Highly Adaptive Lasso and Causal Inference. Mark, thank you very much for joining us today.
For the introduction. All right, so today's talk will be about the Highly Adaptive Lasso in Causal Inference, but more general, just as an estimation method and an ingredient for all kinds of estimators in causal inference. This was jointly prepared with Rachel and some help of Lars. Let me see. Go to the next. Oh, there we go. So first, go back to what is the Lasso estimator. I mean, this is an estimator which has been used, is popular in the machine learning literature. It's just a regression, mostly a regression method, but it's also used for other things like graphical models, density estimation stuff. You would put a logistic or linear model with many covariates, and you would obtain the maximum likelihood or the minimum least square coefficients is bounded by some constant, and then you choose that constellation. So in this way, you can handle many variables than sample size and obtain a regularized maximum likelihood or minimum least squares estimator. The disadvantage of the typical way the traditional Lasso is done is that it relies on these parametric forms. For example, only including the main terms of the covariates, and thereby restricting the actual functional forms and thereby missing the truth. So Highly Adaptive Lasso comes from actually a very general perspective, I will talk about in a moment. But really from a Lasso perspective, it just comes down that it includes a massive amount of basis functions. And so in the regression context, we would be fitting a logistic or linear, whatever link function model in millions of basis functions, spline basis functions, tensor products of spline basis functions. And then the L1 norm is then represents essentially the variation norm of the function. And so the best estimator under this L1 norm constraint. So you find the best fit of the true function under the constraint that the variation norm of the function is restricted. And then, of course, that L1 norm can be selected with cross-validation. The advantages are that Highly Adaptive Lasso is an estimator which, just like a maximum likelihood estimator, has the property that if you use it for computing, for estimating features, then it's actually asymptotically efficient. And in particular, you can also incorporate into target maximum likelihood, and you guarantee you obtain efficient estimator under essentially no conditions. And this is due to the fact that it converges to the true function at a rate n to the minus 1/3 times log n to the power d over 2, where d is the dimension of the function you're trying to learn. So the dimension kicks in a very minimal way through the log n, and so you essentially always get the rate n to the minus 1/3. Which is very fast, certainly in multivariate function space, and in particular, it's faster than the typical n to the quarter you need to obtain guaranteed efficient estimators. As we'll see, it accommodates many variations because you can restrict your function space, and that gives then all kinds of Highly Adaptive Lasso type estimators, and we can choose among them. And the assumptions are very mild. You're not really relying on smoothness. All you rely on is that your true function is right continuous left-hand limits and has a finite variation norm. So which means it can even have jumps. So it's extremely mild regarding smoothness. So the way highly adaptive lasso came up was in my work, where I was interested in constructing a generally efficient targeted maximum likelihood estimator. And I was thinking about what happens if we maximize the likelihood, or more generally, some kind of empirical risk function like least squares. If we maximize that over all functions, where the only constraint is that they are right continuous left-hand limits, which is like CDFs, catalog functions they called, and have a variation norm bounded. And now that class of functions I happen to have worked with a lot in my career early on, already as a PhD student, and it's a function class, which is also used in empirical process theory and so on. So it was a very powerful class of functions I was aware of, but in particular I was asking this question: suppose I just use it as my model, really, which is a very big model, and is that enough to already get decent estimators? And so then it happens to be that that's indeed the case. But essentially, the variation norm of a overfitted function will, essentially track the data and therefore has a variation of order n sample size. By restricting it, you don't allow that to happen, and by making it bounded, and then it just looks for the best fit of the data given that restriction. You can choose that with crossways to get the optimal bias variance trade-off, and you get a beautiful regularized type maximum likelihood estimator. Idea is that these functions, which are all you require, is that they're catalog, right continuous left-hand limits, multivariate real valued functions. You can represent them as an infinite linear combination of tensor products of these spline basis functions, right? So you have, for example, if you have a function of x1 and x2, you would have an indicator x1 bigger than a cutoff, and for all kinds of cutoffs, an indicator x2 bigger than a cutoff for all kinds of cutoffs. So functions which they stay 0 and then jump at the not point to 1. But then you can also have tensor products. You can have indicator x1 bigger than a cutoff times indicator x2 bigger than a cutoff, right? And then, of course, you can do that up till the dimension of the data. So you have these two-way basis functions, 3-way, 4-way, and so on. So they represent like interactions. And on top of that, so that's one so-called representation, that any function can be represented as this infinite linear combination of these tensor product basis functions. Then on top of that, if you then look at the actual L1 norm of all the coefficients in front of these basis functions, that happens to represent the actual variation norm of a function, which you can formally define. Essentially, how much that goes up and down, but then also in higher dimensions. And so, yeah, and that means then suddenly that even though I didn't think at the time about that, I didn't think about lasso, I was just thinking about maximizing the likelihood over all multivariate real valued functions under that variation norm constraint. It happens to be that to implement it, it is nothing else than maximizing over a linear combination of these basis functions under an L1 norm constraint on the coefficients. So in the end, it becomes a lasso problem. It just happens to be that the number of basis functions is massive, to the point of n times 2 to the power d, or d is the dimension. Now with this estimator proving its result, n to the minus 1/3 rate of convergence, I could then prove in this 2070 paper that a targeted maximum likelihood estimator, which uses this to get its initial, nuisance functions like your outcome regression or your propensity score, will now be guaranteed to be asymptotically efficient. Due to this n to the 1/3, you essentially have to deal with the remainder, which is second order, and it becomes then n to the minus 2/3, and that is smaller than the square root sample size, and so it goes away. And so in the end, your maximum likelihood estimate, target maximum likelihood minus truth, behaves like an empirical mean of the efficient impulse curve, and thereby is a fully efficient estimate. And this all under essentially no smoothness assumptions. So it's not just a very theoretically powerful algorithm. It's also actually just very good in practice. And here are just some simulations David Bankser did at the time, where he compared highly adaptive lasso for up to dimension 1, 2, 3, 4, or something, 5, I believe. And then he compares it here with gradient boosting, random forest, kernel regression, and support vector. And just for a free sample size, it is more choice of data chain distribution. And you see, it ends up at the top doing better for each sample size than these other algorithms. And of course, that depends a little bit on what the underlying smoothness of the function is, but it's always right there, performing very well. Here you see an example of how it kind of works. Here's a one-dimensional regression trying to do, and the variation norm of the true function, which is how much it goes up and down. When it goes up, you add it up, and then when it goes down, you add that again. And so you add up all these increments of the function, and it ends. And that's the variation norm of the true function. And if you now fit this regression with like forcing the variation norm to be 4.8, yeah, that's too small, and then you get a kind of a smooth function. You see that with the dotted line, which is missing out, right? Some things. Once you make it 13.4, you get already a beautiful fit, and that's a little below the 16. The true variation norm. It might miss a few things, but that asymptotically will start happening as sample size increases. And then if you go too far, then you're just overfitting the data. And that's like the 35.2, where you start responding to little things in the data. But of course, the beauty is with cross-validation, known to be an optimal method for selecting these tuning parameters, it will figure out how to do that in an optimal way. And so you can be counting on that, and that it will make the right trade-off of bias and variance. In other words, the right trade-off of how complex the fitted function should be. Now, when you fit a highly adaptive lasso, for example, suppose you fit a function of 10 variables, then in principle, if you include all the basis functions, you end up with n times 2 to the power 9 basis functions. Now, that can add up to quite a number, as you can imagine. So that's why the computational complexity is not particularly trivial. But there are there's a lot of computational work and things get better and better, so. But on top of that, there's many ways to restrict the function space, and so it really just comes down to which basis function do you want to force to be included. And so, for example, here are a few examples where you can use as a screening to say that these basis functions are just indicators. And so once they become very sparse, so they are just 1 zeros, if they become very sparse in the sense that there are very few ones or similar very few zeros, then it becomes like a basis function which is only needed when sample size is very large. And so basis function, you could say, why don't I get rid of that? So I'm screening out all the basis function with a proportion smaller than some cutoff. So that's one way to have another screening parameter beyond the L1 norm, which then forces you to have many fewer basis functions. And then with cross-validation, you can still tune that. And in particular, this allows you then to only do the fit for increasing number of basis functions. And when you see that the cross-validated performance goes down, then you stop, because then you don't have to fit the full-blown with all the basis functions, because you already know it's already at the point where it's not helpful anymore. And therefore, computationally, it becomes now very doable. And you would only go to these massive fits when the sample size is very large and requires that. You can also enforce a maximum order of interaction, like how many do you go up to 1 ways or 2, 3 ways. Particular additive models, you can say I only want, bivariate functions of this treatment with covariates, but the covariates, I want them to be just as purely additive functions. You can of each function. You can also make it smooth. There's also this higher order spline representation of these functions, but then now you're assuming some smoothness. You can also discretize the continuous covariates, because they are the ones contributing a lot of basis functions, a lot of knot points. You don't really need that, right? If you have a continuous covariate, 5, 6 knot points is already pretty good. So you don't need n of them, which is what it would do if you don't restrict it. And then on top, we have these greedy screening algorithms where you first fit the HAL with only the 1 ways. And that will at most select n basis functions. Then with these n, you construct the 2 ways interactions, and then you fit it again. And so in this way, you can build hierarchically more and more complex function, and at the end, stop when it is not helpful anymore. So here's an example of the R package we currently have. It's called HAL-9001. You can load it with this command in R, and you need to create a dependent variable, like if you want to use it for the sake of regression. And what we're doing here, you create this covariance design matrix with a bunch of variables. You simply run HAL fit is fit HAL x is x, y is y, and that is the simplest one, and that has defaults obviously. And this would go up to three-way interaction and no restrictions on the base functions, but there is to restrict it. So here are some examples of that. Suppose your data is W1, W2, and let's say a treatment and an outcome, where W's are the covariates. You can specify that you want a certain functional form. For example, you say, I want a pure additive model. So then you can write Y is dot, or write it out as Y is HW1 plus HW2 plus HA. So that's a pure additive model, and it would then fit that each function with all these splines, and so that will only allow you for one-way basis functions, and thereby fit an additive model. But you can also do a bi-additive model where you say, I want all two ways, and so you can do that very shortly by writing down dot to the power 2. But you can also just write it out. You can say, I want HW1 plus HW2 plus HA, but I also want a function of W1 and W2, and I want a function of W1A and W2A. And obviously you could leave out. You can also say, I want only interactions with A. So you can write that as Y is H dot. So that's an additive model just in as one-dimensional functions, and then plus H dot comma A. That means it adds all the two-dimensional functions with A only. Right? And so if you would write it out, it would be written like what we do there by writing HW1A plus HW2A. So in this way, you can choose where you want real effort for fitting maybe the interactions or the effect modification. And then you can also specify that you want certain of these functions monotone. And so you have I for increasing and D for decreasing. And so here's an example of Y is IW1 plus DW2 plus IA, meaning it fits an increasing monotone function W1, a monotone function A, and a decreasing in W2. You can also specify S is 0 is the default, and that's the one where you don't need any smoothness, and it has these indicator 0, 1, jumping from 0 to 1 basis functions. Here is examples of an additive model and a bi-additive model with not points, 0.5, 0.3, and here an A, if A is binary, then you have naturally only one not point. But if you want first order splines, you can specify S is 1. And then you get these first order splines, which are of the form like indicator W bigger than 0.05. So that means it's 0 up to 0.5. And then instead of jumping to 1, it goes in a straight line, W minus 0.5. So it becomes a straight line going up. Then you can also specify ways of screening, like you can use bin which really means just discretizing the covariates. And you can also use greedy screening. And for example, here's an example with N is 2,000 observations and the dimension is 12. You can say, I'm not using any binning, then you get the full-blown 600,000 basis functions if you go up to three-way interactions. On the other hand, if you say, I want the one-ways, I want to discretize them in 100 values, which is still a lot, we don't even need that. For the two-ways, so the interactions, I bin the covariates having only 5 not points each of 25. And then for the three-way, I make it 5. So that's a way then to reduce the space of basis functions and thereby end up with only 30,000. And then you can also do the sequential screening, where you first start with the full-blown this is the main term model. You end up then with selecting. So you start then with only 20,000. You fit it. Then it ends up with maximal n. So you end up, and then you work with that to create the two ways. And so here's an example of a data set where we run the sequential screening, and here the no sequential screening, where you just go full blown for the full blown all basis functions. And you see that what you see here, that these screening methods are not necessarily making it worse. In fact, many times they make it better. So it's not, so they're computationally faster, but also actually often in practice have better statistical performance. So that really comes down that HAL is really not just one function, just like many machine learning algorithms. They have all kinds of tuning parameters. That's also the case with HAL. We have lots of ways of specifying all kinds of interesting estimators, as we just discussed. And then the question is, okay, which one am I going to use? And that's, of course, where the idea of superlearner comes in, where we say, you just build a library, in this case, of all kinds of HAL estimators, and you use cross-validation to choose the best one. And so in this way, we can obtain a superlearner, which will then use cross-validation to choose the best HAL estimator among all these HAL specifications. And you will be guaranteed, because of the properties of cross-validation, to really find the right one. And in particular, you're guaranteed to get this rate n to the minus 1/3 if at least that fully non-parametric, most non-parametric one is in your library. And obviously, you can also include other estimators in your library, such as parametric models and machine learning algorithms. Another thing we have been working with is, when you do superlearner, you have this, which is just, you really do a meta-learning step, right? You build your library of algorithms. So that's the first thing you specify. And then you have these algorithms are training samples, and they become covariates at the meta level. So you create then a data set of n observations, you have an outcome column, yi, and then your covariates are the algorithm trained on the training sample, excluding that observation yi. And then for each of these algorithms, so if you have 20 algorithms, you would have 20 covariates, which are all the predictions from that particular algorithm for that observation I, but where it was trained on the training sample, excluding that observation yi. So that's the meta-level data set, which is its own regression. And for example, we use often convex superlearners. There we just find we really fit at that meta level and simply in linear regression, but forcing the weights to sum up to 1 and be positive, for example. And but there's nothing which says you cannot do something more aggressive there. So in particular, what we have been playing with is to actually use HAL at the meta level, meaning you're using the highly adaptive lasso, but where your covariates are these transformations of the original covariate vector implied by these prediction functions, these algorithms. And interestingly, and then what you can do, you can essentially build a library where every element of your library is a meta-HAL, but with a different L1 norm, right? Because the L1 norm is very crucial here. If I choose the L1 norm very small, like 1, it's essentially like the convex superlearner. But if I increase it, it becomes more and more aggressive. And eventually I'm starting to learn any kind of functional combination of all the candidate estimators in my library. And so the key is here that in practice, you can easily be too aggressive, but you can also be too worried about being too aggressive at the meta level. And so here again, cross-validation will take care of that because it will figure out how to optimally tune that meta learning data step, fitting step. So in this way, we are guaranteed to do better than any other superlearner in essence. Here's an example of, this was an example of a simulation where we have a library of kind of a bunch of very simple algorithms. And if you do the convex superlearning, you can only do as well as just taking some linear combinations of these simple algorithms. So of course, you cannot do that well. You still do better than any of them, but you don't do that well. But then if you then run the Meta-HAL superlearner, then it will say, hey, these are just transformations of the original covariates. So I can do a lot with that. I just have to be more aggressive. So it would be using a much more aggressive meta learning step and thereby do much better. And in fact, can do as well as the original HAL on the original data. So this way, you have the meta learning step itself adapts to how aggressive it should be, depending on how biased the candidate algorithms are, or maybe there are already excellent algorithms among them. And then in that case, it will not be very aggressive. That's exactly what it should be. So really what I'm getting here at is that the highly adaptive lasso is a powerful estimator, like a maximum likelihood estimator, which can be used to learn functions such as regression functions, but also conditional densities, conditional hazards. For anything really, we have been able to use this. And but it has lots of applications, in particular in obtaining estimates of causal effects. And one application I'm pointing out now, which is this work by Shortreed and Artefai in 2017. They called it Outcome-regression weighted lasso. So they were interested in, you had a data set like covariates, treatment, and an outcome. They cared about the average treatment effect. And they said, okay, why don't we, one important thing in causal inference, what covariate do you put in your propensity score? And that's a risky thing because, you know, if you put in very instrumental variable type covariates in your propensity score, then your targeting step in whatever double risk estimate you use or inverse probability weighted estimate you use becomes erratic. And so the key is, it's not particularly like that you should only care about fitting the propensity score. It's also about how good is that propensity score for the sake of getting, let's say, target maximum likelihood estimate. How well does it perform? And so we have worked with Susan on collaborative target maximum likelihood as a particular approach for that. But here's an example of that type of thinking. Except kind of nice. That's what they did. They said, okay, why don't we first fit a lasso estimator for the mean outcome as a function of the treatment and the covariates? And then in particular, I can look at the coefficients in front of the covariates. And I'm going to say, I'm only going to include the covariates which had a non-zero coefficient in my propensity score estimator. And in fact, I'm going to use a weighted L1 norm as penalty. So if the coefficient was big in the outcome regression, I'm going to penalize it less in my L1 norm regularization of the propensity score. And so anyway, so this was kind of a weighted L1 norm lasso regression. And they showed good performance in simulations and so on. And so our point is that, okay, that's great. Theoretical property, however, relies on correct parametric formula for that lasso estimator. So why not extend this to the highly adaptive lasso? Right? So we are saying, okay, let's fit the outcome regression with the highly adaptive lasso. So now you get all these basis functions, which are functions of W and A. And in particular, you can extract then from that the relevant basis functions, like for the mean outcome at A is 1 and the mean outcome of given W and A is 0, and take all these basis functions and put them in the propensity score. And then you can still use the weighting of the L1 norm. And anyway, and then you fit again a highly adaptive lasso, but now with the propensity score. But again, only including the basis functions which made it. And which is, and then you can still tune both the L1 norm for the outcome regression. If you make that larger, you would have included more. And you can make that a final important tuning parameter. And that can itself be nicely tuned with our collaborative target maximum likelihood procedures we have developed. And so this happens to give a very powerful way of implementing and target maximum likelihood, but really a more collaborative target maximum likelihood type estimator, but using this particular way of generating the variables in the propensity score through first fitting and highly adaptive lasso outcome regression. And so there's one type of simulation we often use for evaluating how well a method works. That's a simulation due to Kang and Shafer, and they use that at the time in that article to kind of evaluate the whole collection of estimators, including double robust estimators, and in particular pointing out that many of them perform poorly in this particular simulation, which happens to be very challenging. And so it was kind of an argument for saying, you know, maybe these double robust estimators are not always a good idea. Of course, that's not the right way of thinking. The right way of thinking is that this is a challenge, and we want to make sure that that we construct efficient estimators which can handle these challenges. And so that's what of course we have done. So here's the simulation. You have a set of covariates, which are hidden covariates, and then you make your treatment mechanism a simple logistic linear function in these covariates. And your outcome regression is also a function of these covariates, and in this case it doesn't depend on treatment, so the real treatment effect is 0. But then the observed covariates are not these covariates. They are complex functions of these covariates. And here they are written down. So these are not simple functions to learn. And so at the end, all you have are these W's. And we are making it a little more complicated by also adding an instrumental variable so that the treatment, has that variable W5, which is really not important, but it would predict treatment. So if you don't, normally you would select it, right? If you just fit your propensity score, because it looks like an important variable. So it's only by looking at the outcome you can decide maybe, hey, maybe it's not so important. And so here are the targeted maximum likelihood estimator, right, where you fit the outcome regression with highly adaptive lasso, and then also fit the propensity score with highly adaptive lasso. And that's just the standard, let's say if you want TMLE using highly adaptive lasso, very good estimate, it's asymptotically efficient, all that. And here you see some performance in this particular simulation. Now, one way to improve that is to say, why don't I tune the L1 norm of the propensity score with CTMLE? CTMLE is a way where you evaluate how good the propensity score works in the targeting step. How much is it actually improving the likelihood during the targeting step? And so that's a way to select this L1 norm. We have some theoretical results for it, that it actually does a great job doing that. And you indeed see that also in this case, it will actually choose this L1 norm for the propensity score, quite different from cross-validation, because it makes it targeted towards its goal, and you make significant improvements. So that's just purely improving the L1 norm selector for the propensity score. By the way, in these TMLEs, we made the outcome regression misspecified on purpose. So it was all about how good are you doing a job on the propensity score. And so here, that's why it becomes very important to maybe include more covariates in the propensity score. And that's what CTMLE did than what cross-validation would tell you. And then we did the outcome adaptive one, where you do the outcome regression with HAL and then only using the covariates of the basis functions from that into the propensity score and fitting that again with HAL. So that's a way of doing CTMLE in the sense that you use the outcome to decide which variables are most important. And this one will be more likely to exclude the instrumental variable, and indeed it will, and that's why it has drastic improvement. It's actually doing so well that it does as well as if you would be given the treatment mechanism. So that's what we call the oracle estimator. And that it even does as well or even better, actually, than that one. Okay. So this point I already made, right, that if you use target maximum likelihood, where you need to estimate the outcome regression and the treatment mechanism, and this holds in general for many causal inference problems like longitudinal causal inference, where you care about the counterfactual mean outcome and there are multiple time point intervention. You need to estimate all these nuisance functions, such as the treatment mechanism, the centric mechanism, and also outcome regressions. And we could use HAL for that, highly adaptive lasso, because then we are guaranteed to learn the true function as sample size grows and at a good rate. And it's a very robust machine learning algorithm. And as a result, because of its properties, you can prove that if you use HAL for these nuisance functions or a superlearner including the highly adaptive lasso, then you are guaranteed to be asymptotically efficient. The only assumptions being the positivity assumption, right? That there is support in the data, the things that you think don't blow up in that sense, and that the true nuisance functions, the true outcome regressions, functions of the covariates and so on, and the treatment, that they're all cat-like, meaning right continuous left-hand limits, and have a finite variation norm. Now that's really hardly an assumption. So in essence, it says it always will be asymptotically efficient. And so here's then the example for the ATE, right? If you care about the mean, treatment-specific mean, then it would say I need as positivity assumption that the probability of being treated given the covariate is positive for all covariate values, and the true functions of the outcome regression and the treatment are cat-like, right continuous left-hand limits, and have a finite variation norm. So that will be the only assumptions we need, and then the TMLE will be asymptotically efficient. And that will be the plain TMLE, but then of course, if we make it the outcome adaptive one, it would still have that property, except in finite samples, it will even perform better when things get challenging, such as instrumental variables. Now, HAL-TMLE is a very robust algorithm, and the nice thing about HAL-TMLE is that you can now do honest simulations, because it's not like trying to, highly adaptive lasso is not going to, cheat in a way of saying, hey, you chose in your simulation this clever, this smooth parametric model, let me also choose something of that nature, because then I can do better. Highly adaptive lasso is not caring about that. It will just throw in all these basis functions and that's it. And so you can simulate from any kind of standard parametric form or whatever you want to do. It's careless, and it will just do what it does. And so in this way, we can run a simulation where we randomly sample a data distribution by randomly sampling functions of how the outcome depends on the covariate and the treatment, and how the treatment depends on the covariate. And they can be crazy functions. And then once you have specified that, you now can take a large sample, like of n observations, from that data distribution, and then run the highly adaptive lasso and the TMLE and see how well you're estimating that causal effect. And in particular, you can then also construct a confidence interval based on the typical variance estimates we use in target maximum likelihood estimation. And so here in this simulation, you see as a function of sample size that the resulting confidence intervals are getting perfect coverage if we use highly adaptive lasso or super learning, including the highly adaptive lasso. But if you start using other machine learning algorithms, you might be getting to pay a price. Now, this is also a very interesting thing, that by highly adaptive lasso, because it's a maximum likelihood estimator, as we know from parametric maximum likelihood, if you believe your parametric models are efficient for anything, for all the coefficients, right? Any function of the coefficient. Now, that's the same with highly adaptive lasso. Highly adaptive lasso is like a parametric maximum likelihood estimator. Of course, it works in non-parametric models and any kind of huge model, but it has the property that if you care about certain functions of your data, smooth functions of your data distribution, like causal quantities of all types, which are typically, pairwise differentiable target estimates, then the plug-in HAL, simply using the HAL fit, will actually be efficient, except you have to undersmooth HAL, meaning you have to choose the L1 norm larger than what cross-validation would tell you. And you can actually prove, you can use particular selectors which are targeted for that goal. And we have done that. So it has this remarkable property that highly adaptive lasso, actually, even with our targeting, results in efficient estimator of any kind of feature you're interested in, if you undersmooth the highly adaptive lasso. And then you can also say, well, what about if I use superlearner? Now, normally with superlearner, you lose that, right? Even when HAL is included in the superlearner, because you take some convex correlation, you use the property of HAL as a maximum likelihood estimator. And therefore, you start losing this property of still being efficient. However, that's not true if we do the superlearner in a progressive way, and we use the Meta-HAL superlearner. Because then at the meta level, we are a full-blown maximum likelihood estimator. And the key about the maximum likelihood is when you're a maximum likelihood estimator, you solve score equations. And HAL solves a lot of score equations. And in fact, if you undersmooth, you start solving more and more score equations. That's why by undersmoothing, you will be solving essentially all the score equations you care about, in the sense that any kind of smooth target estimate you might care about has an efficient impulse curve, which will be in that class of scores, and thereby will solve it. And that makes it then an efficient estimator. And so that's the explanation. So both highly adaptive lasso as well as highly adaptive lasso at the meta level, where you make your covariance prediction functions from algorithms, both have this property that they are asymptotically efficient for any kind of smooth feature. So it's not even targeted for that. Any kind of smooth feature, it will be efficient for all of them. So it's really quite something. So then another interesting thing about highly adaptive lasso is for most machine learning algorithms, you cannot use the non-parametric bootstrap. The theory doesn't support it because when you sample from an empirical distribution, things like cross-validation and model selection, they start behaving differently. So if you use the bootstrap, for example, for a target mix machine learning like random forest to get its nuisance functions, it will not perform well. And that's why we always have been using influence curve-based inference, right? We know that the estimator minus true behaves like an empirical mean of IID random variables. That IID random variables is called an influence curve, and that can then be used to calculate the sample variance of that and thereby get a wall-type confidence interval. But its bootstrap is nice because, it picks up the second order behavior of the estimator. It actually looks really at the whole variability of the estimate, not just its first order sample mean approximation. And so in a bootstrap would be better. There's no doubt about it, except we couldn't use it because of the theory not supporting it. However, highly adaptive lasso resolves that, because if we use highly adaptive lasso to fit these nuisance functions, HAL-MLE will be bootstrapped, and we can use the non-parametric bootstrap. And so we could now just do things like, we have if we fit the outcome regression and the treatment mechanism with a highly adaptive lasso, we can grab that cross-validation selector. We could fix it at that. And then we could draw 10,000 samples of size n from the empirical distribution. And for each bootstrap sample, recompute TMLE. And now, but then you can just use the highly adaptive lasso already, only looking at the base function you selected on the original data analysis. So thereby making it computationally feasible, because that's only n basis function. So that's no problem at all. And so this becomes then, allows it then to use the actual non-parametric bootstrap in a computationally completely feasible way. And then look at the sampling distribution of your estimator and construct a confidence interval from that. And then another thing we then do is you can say, hey, but what about this initial M for the L1 norm, for the highly adaptive lasso? If we increase that, we might see that the confidence interval will get wider and wider. So we are proposing to keep increasing it till it plateaus, because that's a critical point where you have chosen the complexity of the HAL complex enough that you're not fooling yourself by making the bootstrap imitating a simpler distribution than really the reality. And so, yeah, and then we can actually prove that indeed the bootstrap works, that this sampling distribution will convert to the optimal normal limit distribution. But moreover, you can prove that the highly adaptive lasso, when you sample it from an empirical distribution, it has the same behavior. It still approximates the original way at the same rate of convergence. And so it has very similar behavior under sampling from an empirical than under sampling from a smooth true data chain distribution. And that makes it very robust and thereby allows you to pick up real variability of your estimator, even though you're sampling from this empirical distribution. And here's an example of an ATE problem again, WAY, where we care about the average treatment effect. And we look at two types of confidence intervals. One is where we use the OAL type, so the influence curve, and another confidence interval by actually doing this bootstrap. And then to make this simulation interesting, we have, of course, W, four-dimensional W. What is it? A few dimensional covariates, and then we have a treatment mechanism, and we have an outcome. And the outcome regression depends on the frequency of the sinusoid. So as we increase A1, this will become a more and more complex function of the covariates. And so the variation goes up and up. So if you fix sample size, you keep increasing A1, at some point the function becomes so complex that with that sample size, HAL cannot do a good job. And at that moment, you should see that the wall type confidence interval starts suffering because it's not carrying it. It only looks at the variability of the empirical mean approximation. But that's a poor approximation. It's the second order remainder of the estimator we should care about. And so at that moment, the bootstrap starts outperforming, you would expect, the wall type confidence interval. So that's why we have that coefficient allowing us to increase that complexity of the true function. And so this results then, like for instance, here's a simulation for n is 100, very small sample size, obviously, and we did other sample sizes. But what you see here is by using, first we have the coverage in the first picture as a function of this coefficient. Now the wall type has poor coverage, as you see here, and but what we also see is that if we use this bootstrap-based confidence intervals, and where we have, as I said, we use this plateau method, and we also actually what we did, we pick up the bias of the bootstrap. If the bootstrap has a bias, in other words, it's kind of skewed relative to the estimate on the original data, then we penalize the confidence interval with respect to that bias. So we don't correct, think of it as a bias correction because we don't trust bias estimates. So we just use it as a way to augment the confidence interval. So in this way, we obtain confidence intervals. And as you see, even as the complexity increases, which means the true function gets very poorly fitted eventually, we still keep picking up the full variability estimate and get a confidence interval which has the right coverage. So in this way, we can really move towards finite sample inference, even for small sample sizes, by picking up all that poor fitting which happens, for small sample sizes. And of course, the price you pay, as you see in the next picture, is that the confidence interval get wider and wider. Right here, the y-axis is the width, And as you increase the complexity, your confidence will get wider and wider, and significantly wider than what Walt gave you. All right, so some concluding remarks. So highly adaptive lasso is the first general non-parametric maximum likelihood or minimum loss estimator. It goes for full-blown maximizing or minimizing the empirical risk over this huge class of functions, only restricting the complexity, and that complexity, which is the variation norm, can be tuned with cross-validation. It converges at this remarkable rate n to the minus 1/3 up to log n factors. If we use highly adaptive lasso in any estimators, like efficient estimators such as target maximum likelihoods, we are guaranteed to be asymptotically efficient for smooth, like causal quantities. HAL is also remarkably finite sample robust. Like I already said, you can even bootstrap it. So it has really great finite sample, robust performance. Nothing starts crazy, doesn't extrapolate to crazy values. It's just robust. And that's really a very good thing for example, for the TMLE. It represents a class of estimators, like we already pointed out. So we shouldn't necessarily use the highly adaptive lasso in the most non-parametric form. We should actually build a superlearner with all kinds of HAL fits, getting more and more restricted. And so this way, it is a range of HAL estimators going from highly restricted to maybe only pure additive model to having models with two-way functions and maybe even, and so increasing it. And you can screen in different ways. Like we discussed, we can enforce monotonicity, we can enforce these type of constraints, and then let cross-validation. What's the best one for this particular data set? So in this way, you have a very powerful HAL-based estimator, still able to adapt to the sample size and the complexity of the truth, and also making it scalable. This requires some implementation tricks, of course, because you only want to evaluate the estimators which are highly complex in computationally if needed. Because if you already see that the less complex estimators, which are doing less fitting, already reach a point where things get worse with respect to cross-validated performance, then you should stop. You don't have to again compute these massive computationally challenging estimators. So in this way, we can make it scalable and only use the full-blown computational effort if needed. Another nice thing about HAL, it gives a sparse representation. So it just fits a linear combination of n, maximally n, or actually often like half n or something, basis functions. So it's that way you have an actual analytic function. It's not just you have a bunch of predictions. You have an analytic function, and it's actually represented by at most n base functions. That allows non-parametric bootstrap, and it has many applications. Like we said, we can make the superlearner now immensely powerful with Meta-HAL superlearner. We can use it to do this kind of outcome-adaptive HAL-TMLE. That's like a collaborative target maximum likelihood idea, but in using this HAL technique, so that we avoid having to do some kind of iterative forward selection or dimension reduction or ordering. All these things we have also done with CTMLE, but they are all computer intensive as well, and this one, and also you worry then about not being non-parametric enough. So this is another powerful application, and there are actually other very powerful applications of HAL I'm involved in right now, such as learning the efficient impulse curve based on machine learning, so that we can make the whole construction of these efficient target maximum likelihood estimator completely automated by just essentially obtaining these kind of HAL objects as efficient impulse curves without ever having to do the analytic computations. So there's very interesting developments ahead on that front as well. Okay, so this is the last slide. These are just some frequently asked questions. For example, why are global smoothing assumptions better than local smoothing assumptions? In other words, what is it about HAL? Is one question. People have been very surprised, right, about this rate of convergence n to the minus 1/3. And that comes from the literature, we're all probably, many of us have been exposed to, which is that, you need, in high dimensions, you need immense smoothness of your function before you can achieve a reasonable rate of convergence. And that's because, and these are all based local smoothness properties, like differentiability. How many times are you differentiable? And and these estimators are trying to exploit that, this local smoothness. this is not making, HAL doesn't make any local smoothness assumption. It only says it has to be globally restricted in its complexity. And so it can have jumps, but it cannot go up and down more than this over the whole range of its function, of its domain. And that's the restriction which gives us this rate n to the 1/3. So it has nothing to do with local smoothness. Relying, by the way, that this is rate of convergence in an L2 norm, not in a pointwise or superior norm. And we do have uniform consistency as well for HAL, but you wouldn't get probably that kind of rate. It will be a lower rate. But for L2 norm convergence is all we need for all these causal inference problems. So it's actually the right thing we care about. So if I superlearner library, then why would I include anything else? Now, anyway, this gets to the point I already explained, that we should be building a superlearner library with at least all kinds of HAL variations, and because that creates a very powerful, and it makes it better. Right? Just using HAL with the full-blown, all the basis function is not the best estimator for a given sample size. There's something in between there, right? Which is I don't need 5-way interactions. I only need at most 2-way, and maybe not even all of them. Right? So that's what, depending on the data, that's what gives you the best fit, and that's why you build a library of algorithms and let cross-validation figure it out. You might then ask, do I need anything else? Now, that's a good question. To be honest, I think with HAL we can make a very powerful library, and I hardly see a reason for including other algorithms. But on the other hand, from a principle point of view, I think it's fine. However, again, there's something very nice which I'm also working on, is that by being a maximum likelihood estimator, it solves score equations. By the fact that it solves score equations, it makes it very robust, and it has also good properties for the second order remainder, the target maximum likelihood estimate. So by including other algorithms, you lose that. And so in that sense, there is a price to pay by including other algorithms beyond HAL for some of these. You start giving up on being a maximum likelihood type estimator. Now, on the other hand, that can be solved, as I said, by using the Meta-HAL superlearner. Then we can throw in everything, gradient boosting or whatever, because we are doing at the meta level still highly adaptive lasso. We are still a maximum likelihood estimator, except a maximum likelihood estimator with transformed covariates. So that's perfectly fine. And then you don't lose that property. Now, how does screening basis function affect its rate of convergence to the true function? Like I said, if you include it in the library, you only make it better. It's just one of the options, and cross-validation figures out what's best. And if the best is no screening whatsoever, then that will be asymptotically chosen, and you will still get your rate of convergence at the end. Here's another question: how does HAL compare to Bayesian regression trees? I think that's an interesting question. I still think nobody has really looked carefully at that, so that's something which should be done. For example, practical performance comparison. But I also think there's some theoretical work in BART which probably remains to be done. I haven't heard about their rate of convergence. I just know it's a great algorithm. We have seen it in competitions. It has performed very well. My sense is that it has a maximum likelihood type property. It's like a maximum likelihood estimate, except more Bayesian. So it has probably it's probative solving a lot of score equations. That might explain why it does perform well in competitions, even without targeting. Except, I think there's more work to do there and really understand if that's true. Because, just a few simulations or in data competition is not enough to give us that guarantee. But anyway, I think I would be very interested to understand more about BART and understand also in practice how these two algorithms compare. So that's the end of my talk. Thank you very much for all your attention.
Thank you, Mark, for all that information. If anybody has a question, you could type it into the chat window, and I'd be happy to relay it to Mark. And while you're doing that, I'm going to ask actually many questions, but I'm going to ask a really simple one that not only applies to HAL, but also even just to regular ordinary lasso. So what I got out of this is that, by converting the covariates into all these many basis functions, we can have a very flexible fit. And then we're going to use a penalized regression so that we can actually have a fit that works for our sample size. Okay. So now my question is, once you've kind of done that and you have the HAL model or just the straightforward lasso model, at that point, is there any benefit in taking those covariates, whatever form they're in, and doing an actual, now we just add a parametric model, and so refitting and getting a maximum likelihood estimate of the actual covariates in front of, sorry, coefficients in front of those covariates.
Yeah,
Is there any advantage?
right. That's an interesting question. The way I think of that is all you do there is essentially what we achieve with undersmoothing HAL, right? Like one method of undersmoothing HAL we have proposed is to say, fit HAL with cross-validation first, grab the basis function it's selected. These basis functions give you scores, right, which a maximum likelihood estimator would solve. And so then we say, let's now keep increasing the L1 arm beyond the cross-validation selector till all these score equations are solved at the appropriate level. Right? That's what we think of as a global undersmoother, to the point that now it will be doing a great job for all kinds of features, smooth features, for a large class of smooth features. Now, what you're describing pushes that one step farther by saying, I don't only want it to be solving these score equations from this parametric model, I want it to solve it exactly, right? Because you're actually doing a full-blown maximum likelihood or least squares estimate. Now, that's really not necessary. So my gut feeling is that it might be too much undersmoothing, and you start paying a price which might not be so good. So my gut feeling is that what we are proposing, so yes, it gets to the right idea, which is undersmoothing is important if we care about smooth functions and we don't care about only prediction. And so it gets at that idea, but it doesn't mean we have to carry it out till the point that all scores are solved, which would be like a pure maximum likelihood estimator according to the parametric model.
Okay, thank you. It's 3:59, so I guess we should stop. If anyone has questions, you can email them.
Yeah, don't hesitate to send me questions. I realize I should have left more time, so apologies for that. I didn't track that.
Okay, well, thank you once again, and thank all of you for attending.